work, or for starting the work, it's necessary to define an exploration strategy, what to do. So we have done some work in many oceans, so we have some idea about the strategy. We have to consider several scales, and to consider also specific techniques. For example, we have specific techniques to locate active deposits. The geological setting, I just gave a brief summary of where we are expecting to find vents on a slow spreading ridge. The chemical tracer in the water column, physical tracer in the water column. This is for active venting. For inactive deposits, we have to move to near seafloor magnetic survey, for example, near seafloor electric measurement. Georgie will give some detail on this technique. Chemical and mineral tracer in the sediments. The next stage being the evaluation of the deposit using submersible for observation and sampling, and drilling operation. So I will give now some brief detail on these different scales. So the first step, regional survey, multi-beam mapping, and geological survey. Resolution, 100 meters. 100 meters, so the resolution is not exactly at the scale of the object we are looking for. So it's easy, you have just to go on Google Map, for example, and you see, not clearly on this map, but on the screen is better, you can enlarge, and we normally see somewhere here the ridge. But okay, the resolution is about 1 kilometer, and this is not enough to start a diving operation. Then you have to move to the ship and start multi-beam echo sounding. Multi-beam echo sounding, when you look at the southern Atlantic, so this is a satellite image, we clearly see the ridge. It's close to 1 kilometer resolution. When we look in detail, for example, at the central part, okay, you see that when you enlarge, the resolution is not excellent. You see the ridge, you see the transition fault, but it's not very precise. There are some parts on the Mid-Atlantic ridge, for example, here, when some scientific group did some detailed mapping using the bathymetry from the ship, and they even find 2 hydrothermal sites in this place. There is another place further south where the detailed bathymetry from the ship also exists. So there is some data, but in terms of mapping, there is quite a lot to do and to continue. Then, when you have done the map, you end with a high resolution map with 100 meters resolution. The ridge is here, for example. And you see, for example, here you have a lot of line along the ridge. This is a volcanic part of the ridge. You see a change in the morphology of the ridge on this side. So it's another type of outcrop. This is volcanic. This is outcrop from the mantos. I have no time to go into detail. Just to show that we are moving in detail. So at this first step, one important point to locate the vents is the plume studies. Scale 100 meters to, say, 1,000 kilometers. So to locate the active zones, remember this drawing, vertical output, and the plume is moving around horizontally 300 meters above the seafloor. So it's an interesting point to trace and locate the vents. Look for the plume. For this, we use what we call a rosette system with a CTD. So it's a specific device to measure temperature, dissolve oxygen particles, and to collect water samples. This is operated directly from the ship. And so the picture is not good here. Maybe the next one. It's very dark. So what you should see is we have the temperature here, you have the depth, and what we are looking for is temperature anomaly or particles anomaly. And so you will see better here if we move to this one. So these are vertical profiles. Here you have a series of vertical profiles here. And you see the scale here, 50 kilometers. And you can trace this anomalies concentration of some chemical elements, concentration of particles, and you can trace and draw the plume above the seafloor. But this is not enough, because when you have the plume, you know that they are vents, but you don't know where they are. The interesting point for this plume is to look for the root of the plume. And for example, here we have the plume, we have the ridge, but also we see that the plume is floated somewhere. This means that the vents are somewhere here. So this is a general strategy we use for locating active vents. Another tool we use at this scale, say to 1 kilometer to 1,100 kilometers, it's the side scan sonar. Side scan sonar can give interesting image. First, side scan sonar is towed system near the surface or close to the seafloor. It's not spectacular, it's just like a tube. And this produces interesting data. When you compare this image of the ridge, where you have a series of faults here, a volcano at the central part, and when you will enlarge this on the side scan sonar image, you see here these faults are clearly seen with more details on the side, and you can then use this data for starting and thinking about the diving operation. Then the next step is sampling. So sampling, you will receive more details with Georgie. Sampling for sediments using core system. Sampling just dredging for rocks. And then at this stage, you have not really seen the vents. The second step is diving operation with high resolution survey and precise sampling for biological observation. So we can use manned submersible. We also use ROVs connected to the ship using a cable. This is operated directly from the ship. We can also use autonomous vehicles for multi-beam mapping, for example. And using this different instrument, particularly the ROV and the IUVs, we can produce high-resolution mapping. This is one example of the map we had last year, just starting exploration with a Russian group on the Mid-Atlantic Ridge. And the resolution you can see here was about 100 meters, which is not, it's good to start the work, to trace for the plume, but it's not very precise. And what we did is multi-beam survey. It was the first time I did steps. Multi-beam survey to produce high-resolution mapping near the seafloor, 50 meters above the seafloor. And we end exactly the same place with this type of map. If you move from this to this, you clearly see that you start really to see the thing. So if we enlarge this part, you see this some kind of volcano, 25 meters across. And of course, we went there directly, and we find that this small crater was a very active vent field. So with this type of data, you can start to work very precisely and then produce 3D maps of the vent field, for example, where you can see individual chimneys here. And this is really high resolution maps. And we are just starting to use this type of data on the deep oceans. One example again on the Krasnov field, just to show the size of the field. So this again is high resolution mapping with a resolution of about a few tenths of centimeter, where we have here a volcano, the Rift Valley Fault, a sulfide mound, and this mound is split in two parts, collapsing in the Rift Valley. And part of this mound is here. And when you trace the mound, you can trace the mound down on the Rift Valley Fault here. And we can contour the deposit. And the deposit is about 800 meters and 300 meters wide. So it's one of the largest sulfide deposits we know in the ocean. So this is a high resolution data. Then we can produce a high resolution picture and mosaic of the deposit. And then you start to see the vents. Okay, you have different step, different stage. It's a lot of work. It's a lot of cruises. And then you can start, for example, using this specific device to sample the water and to sample the rocks, of course. Another interesting tools for locating vents and inactive parts of the vents is a magnetic anomaly. Here you have the ridge, a magnetic survey, and the magnetization of the ridge with the demagnetization, so low magnetic anomaly, where you see that the water, the hydrothermal circulation has reduced the magnetic anomaly, and you can locate interesting place just looking at this magnetic anomaly. So the next step may be the scientific drilling. So drilling, for this you use a big ship. It's an international program. And you may drill, for example, this is a tag mount. In yellow here you have a series of lines going as deep as 150 meters. And you can reconstruct the three-dimension view of the deposit. Here in red we have the massive sulfide, and in green the sulfide, but partly replacing the basement rocks. And this is about 4 million tons and was drilled at 3,600 meters of water depth. And the final steps may be the industrial interest and the Nautilus company in the southwestern Pacific. So they used the same tools, but with a different objective, on the Manus Basin here near Papua New Guinea. And they use ROVs. They use a drilling ship to collect cores from the seafloor. And they now are planning to build a ship to mine this deposit by 2010. And for estimating the size and the value of the deposit, they had to use a drilling system directly on the seafloor to produce high quality cores, to estimate the concentration of the different metals, and you see here the deposit, the scale 200 meters, and the number of cores it did to estimate the size and the composition of the deposit. And then with this type of drawing, with a three-dimension view of the deposit, indicating the thickness of the massive part, and of course the composition and the interest in copper and gold. And they are thinking about different techniques to extract this from the seafloor. And so to end my talk, I want just to remember and not forget that this is always a multidisciplinary story, and also an international story. This is just a picture of the group we had last year on the French ship. It was a French-Russian cooperation, but this was the end, or not the end, the continuation of several years cooperation when we had a Russian ship, and Georgi will detail the data in this place. And just to show that this is a very interesting story in this term, international and multidisciplinary. And just to finish, that somebody wrote some time ago that in the ocean depths there exists mine of zinc, iron, silver, gold, which would be quite easy to exploit. And this was written in 1869 by Jules Verne. So, thank you for your attention.
Okay.
So Georgi will continue the story, but focusing more on the work on the Atlantic. And at the end of his talk, I will show, for those who are not familiar with Vance, a short movie, 7 minutes, just to show you what you see when you are diving there. Thank you.
The Institute for Geology and Mineral Resource of the Ocean, Russian Federation, and the Institut Français de Recherche.
The ocean, the Achadze field, where you see here the clear smoke coming out at about 100 degrees. And this, say, low temperature fluid for us is precipitating mainly zinc sulfide. Zinc sulfide are forming, say, about 100 and 250 degrees. And you can see here anemones, shrimps. And so this is a cold part of the vents. Then when you move closer to the hot part, you see this black smoker, very active. And this is bringing at the seafloor fluids at temperature exceeding 350 degrees. And to transport and precipitate copper, for example, you need temperature higher than 300 degrees. So this smoker are directly precipitating the copper sulfide there. And one point interesting and important is that to transport copper, you need 300 degrees. That means that sea level, where we have a maximum of 100 degrees for boiling, you cannot transport and precipitate gold or copper. This means that to see interesting deposit in terms of zinc above 100 degrees and copper, you need to go deep.
So the animals around are very interesting. For example, these shrimps, they are blind, but they have such an organ as a heat radar. So they are looking for the warm water using this instrument inside of their body.
So I'm sorry, the movie on the screen is a little bit dark, but it's not always easy to get a good movie of black smoke on a black background. It should be lighter. But of course, black on black, when you are diving, you just see the black smoke from a few tenths of meter when you are diving. I remember diving with Nautil and passing say less than 50 meters from a very active black smoker, and I've not seen the black smoker. Here again, clear smoke. We measure the temperature here, and this was 98 degrees exactly. So 98 degrees, this is a good temperature for thermophilic bacteria, because we know that in those sites there are interesting bacteria that can live in really extreme environments, because here extreme is temperature of the fluid, extreme is the pressure, 4,000 meters, extreme is the concentration of metals. So we are really in those places where we can see the extreme of life on Earth. And here we have a series of tubes where in here and there you can see that you have the living animals inside the tubes.
What the chemical composition of the
Smoke?
Yeah, the smoke.
So the smoke, we say smokes, but it's not gas. It's just water mixed with water, because it's not boiling. We have no gas. But the water in some vents, when you see the water coming out, you see that it's completely clear. And it starts to be black just a few millimeters, centimeters outside of the vent, where it starts to mix with the seawater. And when it starts to mix with the seawater, you start to precipitate the metals and the minerals. So the black smoke is copper sulfide, zinc sulfide, but also calcium sulfate. So it's a lot of tiny mineral particles. So here we change the zone. We move further north, 3,000 meters of water depth at the Logachev site, where in one spot, it's not like this everywhere, but in one spot we have really a high density of shrimps here. You can see them swimming in the hot water, but also at this place we had a lot of living mussels. So you see the shrimps. So some people, there is a general question when people look at this picture, they say, do you have tried to eat the shrimps? Do you have tried to eat the mussels? So some scientists have tried. I've not tried myself because me and probably Georgi, we know that in this environment there is a lot of copper, zinc, of course, but sometimes lead, sometimes arsenic, antimony, cadmium. So all these interesting metals you don't want to eat. But those people who have tried to eat, for example, the mussels, they were not sick the next day, but they have not tried another time. So here you see some fish, some small starfish.
It's very interesting that this concentration of life and background for this, like a desert, so nothing life around. This is only few hundred of area which such a concentration of life.
So here some gastropods. So gastropods and the starfish are feeding on the dead mussels. And probably we forget to mention about life, that this life is completely independent from the sun. The energy is not coming from outside, but the energy is coming from the earth. Say it's for biology some kind of geological energy, because the starting point for this life is dissolved elements such as methane, hydrogen sulfide, hydrogen, and this the bacteria are feeding directly on this. So here you have a clear smoker where we have in this place boiling.